A siphon usually refers to a tube in an upside-down U shape that allows liquid to flow from a higher reservoir upwards into the tube and then downwards into a lower reservoir without the continual use of a pump. In order for a siphon to begin operating, an initial external pump has to be applied to allow liquid to begin flowing through the siphon, but the pump doesn't need to be used repeatedly for liquid to continue flowing through the siphon. Siphons are commonly used in flush toilets, crop irrigation devices, wine fermentation devices, and many other devices that involve the transfer of liquids. Those siphons have been used by the Egyptians beginning in 1500 BC. Physicists still haven't completely agreed on how siphons allow for water to flow upwards against gravity without the continual use of a pump. One theory explaining the siphon is the chain model. This is the concept that a siphon can be modeled as a chain hanging over a pulley with one side of the chain on a higher surface than the other side. Since less chain is over the higher surface, the chain over the lower surface is heavier and pulls the entire chain over the pulley and onto the lower surface. The chain model displays that the conservation of energy isn't violated in a siphon because liquid is pulled like a chain from a higher point to a lower point due to the force of gravity. However, the chain model isn't completely accurate because the weight of the liquid on each side of the siphon doesn't matter like it does for a chain on a pulley. For example, if the shorter side of the siphon had a much larger diameter than the other side, and thus the liquid in the shorter side had a much larger weight, liquid would still flow from the higher reservoir up into the siphon and down to the lower reservoir. Thus, the chain model isn't strongly agreed upon. Another explanation of the siphon is that it uses tensile strength to pull liquid over the top of the siphon. Tensile strength is the resistance of a material to break under tension. This explanation argues that liquid won't break at the top of the siphon and continues to flow through the siphon due to large tensile strength in the liquid. However, siphons have been found to not need any liquid tensile strength to function, such as when there's a space interrupting the liquid. They also argue that liquid has positive pressure through the siphon, so liquid molecules actually repel each other to resist the pressure instead of pulling on each other. Unlike the previous two explanations, the most widely accepted explanation of siphons argues that the pressure on the liquid on each side of the siphon matters instead of weight or tensile strength. It argues that a siphon works because gravity pulling down on liquid in the taller side of the tube leaves reduced pressure at the top of the siphon. This pressure that is lost is known as hydrostatic pressure when the liquid isn't moving. Hydrostatic pressure is the pressure exerted by a liquid at equilibrium at a given point within the fluid due to the force of gravity. With this reduced pressure at the top of the siphon, atmospheric pressure pushing liquid up into the siphon outpowers the force of gravity on the liquid in the shorter side of the siphon. Like objects which tend to move from points of high energy to low energy, liquids in a siphon tend to move from points of high pressure to low pressure. Therefore, liquids flow from the higher pressure area at the higher reservoir up towards the lower pressure area at the top of the siphon and then down towards the lower reservoir on the other end of the siphon due to gravity. Opposers to this explanation argued that atmospheric pressure can't be pushing liquid over the top of the siphon because atmospheric pressure is nearly identical on each reservoir on each end of the siphon and should cancel out. However, supporters to the explanation argue that the force of gravity lessens atmospheric pressure's effect on each end of the siphon, and that pressure from the lower reservoir is cancelled out more by gravity. They use a cart model to back up their explanation. They argue that the side with 300 newtons on the cart represents the longer side of a siphon, while the side with 200 newtons on the cart represents the shorter side of a siphon. This model shouldn't be taken so literally, though, since weight of liquids on each side isn't a factor on a siphon. Rather, atmospheric pressure on this higher reservoir is less cancelled out by gravity due to its height or distance to the top of the siphon compared to atmospheric pressure on the lower reservoir. I hope you've enjoyed this presentation of how your toilet works.